Hey nerds! Welcome all to STAR's mission with SPEX, space exploration. Mission. Just a few opening announcements before we start. You know the drill. Membership is $6 for the rest of the semester. Not a whole lot of it left, but there's still plenty of perks you can get with it. You can get discounts on the T-shirts. You can vote in the upcoming elections, or you can run in the upcoming election. You can also spend $1 and drink some of our wonderful sodas over here. I believe if it's the same as last time, we still have Sprites and Pepsis in there. So drink up. All the proceeds go to the IDPF. I'm Carrie Fisher. So talk to Tulio if you want to get any of those. Coming up this weekend is going to be Toricon. Sure you've all heard of it. Star's going to be there running Artemis. And Artemis is Spaceship Bridge Simulator. Basically, it's like, you ever watch Star Trek? It's like you're playing Star Trek. Same sort of thing. You're on a ship, you're flying it around. It's really fun. So stop by. Yes, Zachary?
Is anyone in Star, like maybe like that guy and that guy, doing anything else at Toricon?
They are. Let them talk about it.
Yeah, they are. I'm going to let them talk about it. Who else? Is anyone else doing something fun at Toricon?
There's an awesome show you should check out that happens on both days, where you see a bunch of fictional characters fight each other in a fictional game of chess. We have all your favorite characters, like Sherlock, Sweetos, Scarecrow, and more.
That sounds cool.
You just went with 3 characters who are like barely sci-fi and not anime when talking about an anime convention at a sci-fi club.
Our characters. All right, and members of Star is also in it.
Wow.
That's true. That's amazing to hear. You should totally go see Cosplay Chess. Now, just another go around. Is there anything else that anyone here is doing at Toricon that they want to plug really quick? So
You should check out the workplace competency panel. We'll tell you how to be good at your job, maybe.
Cool. I could go do that. Also, this Wednesday, PR committee, as per usual. Things aren't really going down there, but if you have, except like we're not doing a whole lot of work this week, but what we are going to be doing is a PR point redemption. So if you got PR points that you've earned from doing PR work for us, like postering or designing posters, you can trade them in. Be giving out T-shirts, be giving out little prizes too, or if you have enough, can exchange them for a ticket to Infinity War, which is going to be our next movie outing on April 27th, 7 p.m. Same time, same place as usual. And Tulio, are the tickets pre-orderable now? Well then, if you have a membership, talk to Tulio to get your tickets bought through us. Now, without further ado, I'd like to hand it off to our friends at SPEX for their mission.
You guys, what's your favorite space, like fiction, space movies? And Star Trek obviously is what I'm feeling a lot of. I'm a Star Wars fan personally. You guys can see me later. Because James is gonna go first and present some stuff, and then I'll go second and present some more stuff. But you can boo me later in that.
Future all number space?
Yes, I'll count it. Rick and Morty, I'm a Rick and Morty fan as well. Anyone else got any?
Moments from space?
At that point, you're going to say Spaceballs at that point.
Also things from space.
Alright, what do you got over there?
Ultron.
I heard that's good. I haven't seen it though. Alright. With that stalling technique though. I'll pass it off to James.
Hey guys, thanks for inviting us here today. So we're going to talk to you about a couple projects that are coming up at NASA. Really cool, and they're real projects. These projects have been funded at least for a phase 1 NIAC study, which Amber did over the summer. She's going to talk to you about a couple of things that she was really heavily involved in. I'm going to throw a couple of really cool projects at you that are currently being investigated by people at NASA or funded by NASA for the first phase of the NIAC, which is about $200,000 of funding, I think, around there. So they get a good amount of money to really flesh out these ideas, and they're more like feasibility studies to see if this is really possible. And if it is, and it's really it's got a potential for doing something really interesting, cool, and beneficial for society, they go into phase 2 and phase 3 and yada yada until they get funded for a full mission. So the first one that I'm going to talk to you about is a radioisotope positron propulsion system. This is basically antimatter propulsion, and it's real. So there's a team at I think Berkeley or some California institute is doing a project on this, and basically the reason that they're investigating this is because they have figured out a way, or theoretically figured out a way to create a pool of antimatter, positrons, antiprotons and antineutrons and such that can actually get around the fact that with most propulsion systems you need to have a tank of the matter in one spot and highly pressurized so that you can use it efficiently. Where this would use some really complicated physics and electromagnetism to create these particles from the matter around it. And it would be able to propel itself using much less weight, and that would increase the payload mass that they're able to travel. Yeah.
Does the electric field used to generate this, does that also generate by the matter reaction?
I'm not totally sure. I think they actually there's a project, a picture of the project on the next slide. So this is basically what they're thinking. I'm not sure the answer to your question, but I think they actually have an external electromagnet that they're using to fuel this entire reaction. But basically what they're doing is, one of the biggest reasons they're doing this is to do asteroid mining, because what they would theoretically do is land on the asteroid and then be able to propel themselves off with carrying as much weight from that asteroid back with them as possible. And of course, the more we can do that, the better. And that's really, I think, what they were going for with this. But of course, this has other potential for different missions. It's always great to have a bigger payload mass that you can carry around with you. More science, more data, or everything. So this is a approximate model of what they're looking at. So you have the asteroid interaction system here, the payload with a fueling station, the positron source and moderator, and the radiator, the enrichment, and the buncher and focusing, and then the nozzle. And basically, this is how it propels itself. And so this side is propulsion, and this side is asteroid interaction. And as you can see, this is a very high-level overview. It doesn't go into all the details, because at this point, what they're really looking for is this possible? Can you theoretically do this with the materials at hand? And that's a really big question. And before they do anything else, they need to answer that before moving on. So this is in a phase 1 study right now, and it just got funded, I think, in early April, maybe late March. So they're just diving into this now. Hopefully, in the next few years, we'll be floating around on antimatter propulsion systems. If they really get this going. Either way, hopefully, we will see it in some way or other in space exploration, getting to different planets or different celestial systems. And yeah, so that's a really cool idea. Just if anybody's unclear what I mean by antimatter, these are not mystical particles that float around doing anything and everything they want at all times. It really is quite simple. Antimatter are electrons, protons, and neutrons with all their physical characteristics flipped in a sense. And that electrons, commonly dubbed as positrons within their anti-profile, is a positive charge and an opposite spin. So spin is a very complicated fact of angular momentum of quantum particles that I'm not going to get into, even though I know many of you want me to, but we'll be here for a while. So basically, the only thing you really need to understand about these is that for an electron, you have a negative charge. For a positron, you have a positive charge. for a proton, you have positive charge, antiproton, negative charge. And that's kind of the idea that we're looking around here. And the basic, I stole a sentence from their article. The goal of this effort is to determine the feasibility of a TRL-12 radioisotope positron catalyzed fusion propulsion concept that does not rely on trapped antimatter. And that's basically the biggest part of this project. If they are able to create a propulsion system that doesn't need a bunch of the propellant in one place at all times, that takes up a lot of mass, they, one, have a very interesting type of propulsion system and also a very interesting concept in general. Another mission that's really, really interesting that was chosen for a phase 1 NIAC study, and they were given the same amount of money, is an interesting take on a balloon. So as you know, as you may know with balloons, the way they function is by having a less dense gas and a higher density gas. So with helium balloons, the ones you may see at parties that are filled with helium, helium's a heck of a lot lighter and less dense than air, so it floats up. And that's basically the whole idea of balloons and how they go up and stay up until they're up. But for anything else, really all you're really looking for is something that's less dense than the things around us. And for Earth, having an evacuated chamber made out of metal would put way too much pressure on the outside, and no known element would be able to stand that pressure. To have a significant, so if you had one of these that was this big, maybe it could, but the lift you would create from that is not nearly enough for any really cool science. And they've estimated with the payloads that they would want to send up, the mass limitation would be significant if they needed to keep their radius to a point where the force created by the atmosphere was such that they could actually have materials keep themselves rigid and not collapse in on each other due to the high pressure. Because even though 14.7 psi pounds per square inch sounds like a little bit, when you have 1,000 square inches, it's a lot more. So things like that inhibit what we can do here on Earth, but for Mars, that's a whole different story. So what they're thinking is for Mars, it would be really, really cool if they were able to land something on Mars and have it send up a sample or a payload into the sky so that it could float around Mars at its own will, do whatever it needs to do. And the really cool thing about this is that there's no propellant. It's just a vacuum. So all you need to do is pull everything out. You just need a pump everything out of there. So if you need to land for repair, you don't need a certain amount of propellant. You just need a certain amount of power that you can gather from solar power. And that's really interesting and really cool because NASA's been looking for something like this where they're able to do constant repairs or constant maintenance to keep it up to date and keep it going for as long as it possibly can. And this is an actual possible mission that is being investigated. Hopefully we see something like it. But basically what they're thinking at a very high level is that they would have this evacuated space in the middle of the payload. It would be spherical to maximize its strength. And then there'd be a sort of lattice structure keeping the inside and the outside rigid while maintaining structural integrity. And then you'd have your inner shell and your outer shell. And those would really, that's where a lot of the stress would be on the material. And it's really important for them to keep that rigid so that it doesn't collapse in on itself, because that's what vacuums want to do. They want to collapse. The reason we can't do this with balloons is just that with a balloon, if you take all the air out, it just collapses into nothing. So you need a rigid structure there to resist that collapse. And then when you put it into air, assuming that it doesn't collapse on itself due to atmospheric pressure, it would rise to the point where the pressure is equal. With a vacuum, that would be space. So it's theoretically able to lift itself to space and come back down, land, repair, and then evacuate its chamber and go back up. That's a really interesting proposal that they've really liked and are funding for another phase. And I think this one has been is starting to go through phase 2. I'm not 100% sure, but it is definitely passed through its phase 1 concept study. So there is an obvious benefit over balloons. With balloons, you need propellant. You can carry helium to Mars. You can carry whatever propellant you want to Mars, but you only have that much. And once you use that up, you're kind of just on the ground forever. So that would get around that ability to have a rigid structure. It puts in all these different things that you can do, like the repair and the maintenance and the refueling, so to speak, as it goes down and comes back up at its own will. And it's much easier to work with. And the science that they could do with that would have much more merit than something that would have a limited lifespan due to the propellant inside. And if a balloon pops, that's kind of it. If this pops, which it could, it's the same deal where it's not useful anymore. But having a titanium structure is much less likely to pop than a latex structure, which is what balloons are commonly made out of these days. The other thing is that we talked about, I think, for anybody who was here last year, yeah, sorry.
I had a question on the last one.
Sure.
So, I guess I kind of don't understand. Like, does this have the same similar drawbacks to a balloon in that like it couldn't be used as a substitute for VTOL?
VTOL. The problem with VTOL is you still have that propellant that's required to lift itself up. And one of the biggest points about this here is that it doesn't need propellant. All it needs is the mechanical function to bring itself back up. And it is not a substitute for VTOL, because VTOL you could lift off the planet and just go. To be able to do that, you would have to have an external propulsion system to actually exit the planet's gravitational influence. But it could definitely get you high enough that you could do atmospheric science, maybe seismic science, anything, including Mars's gravity. You need to be isolated from it directly, because when measuring some sort of activity at these interactions between some things where maybe it's particle interaction, vibrations from the actual planet can throw that data off significantly. So getting up off the planet is definitely the best. And even with VTOLs, there's many considerations that need to be taken into account in terms of mechanical stresses and things like that. But no, it is not comparable. All right, two different things. You would use them for two different applications. Any other questions? Sorry, I'm going too fast. Please let me know. Good. Okay. So solar sails. We talked about this a little bit last year. I didn't want to talk about it for too long in case any of you were here and might get bored of this. But basically, solar sails work using a very more well-known concept these days, as it's really coming now. But for any of you who do not know, photons can impart momentum on whatever they hit. Now, the photons impart very little momentum, and and the more area they hit, the higher the momentum transfer. So with these solar sails, the only reason they really work is because they're really huge. You sitting in your seat getting hit by that projector light is not going to do nearly anything. It'll be very negligible. But with these solar sails, they're outside of Earth. They're using these solar sails as a primary method of propulsion for station keeping purposes. They are not being used for transmit purposes quite yet. I do not think. The problem with this being that you're limited by the wavelength of the photons hitting you. Can't really do much about that except making an artificial photonic influence like a laser, and we will talk about that. But for now, really, I just want to introduce the theory. There is an energy momentum equation that governs this. It is called the energy momentum equation. This is its form. It's the energy of the particle squared times the momentum of the particle squared times the square of the velocity, the speed of light, the square plus the square of the mass, and the cube of the quadruple of the speed of light. And this is why some people can kind of get confused, is because although they do not have mass, they can still impart momentum. So the fact that they do not have mass lets you drop the second term here, and you get a much more simple equation where your energy equals your momentum times the speed of light. That's a very common equation you'll see if you ever take a physics class, like Modern Physics 1 or Modern Physics 2. You'll see this quite often. It's a really, really important equation for photonic physics. So basically what happens here, I made a small diagram, and there's much better ones that we'll get to see, but the photon comes in at an angle here in this diagram. It'll come in at an angle, it'll bounce off and go this way. And assuming this is a perfectly reflective surface, I couldn't make it white because then you couldn't see it, but It's perfectly reflective. All the momentum of this photon hitting this plate will drive it that way, and the photon will head the other way. And beam of light having multiple photons, this will occur with every photon that hits the plate. And the reason that we use this is for CubeSats. And we'll take a look at that other slide in a second. But this is an application that has been very highly theorized and actually applied in a few cube satellites. Is everybody here familiar with cube satellites? Am I speaking gibberish?
Is it
I know what a cube satellite is. Okay.
Is it that thing on the screen?
That is the thing on the screen, yes.
Okay.
So this is the solar sail. This is the cube satellite here. Cube satellites are very small satellites, specifically made for experimentation of new technology or some sort of science. Sometimes CubeSats are made for doing specific research, but mainly what CubeSats have been made for are for university teams like RIT SPEX to create an experiment and test it in space in a low-cost environment. So a cube satellite is a form factor of 10 by 10 centimeters, varying with 1U, 2U, 3U, all the way up to, I think there have been 24U. But it's basically just 10 by 10 by 10 is 1U, and then you just add those to get 3U. It's just 3 of them stacked on top of each other, and then they start going sideways. So 3U, 3U, so 6U. But that's basically the idea. And they're really, really small, 10 centimeters by 10 centimeters by 10 centimeters. As you can imagine, isn't a whole lot of space for science. It's about like this big. So it's big enough to put PCBs in, it's big enough to put very small mechanical instruments in, but it is not big enough to do these crazy, huge experiments. And that's why we do them, is because they're relatively cheap. We can machine CubeSats on campus here using the technology we have available to us. We can. It's very, very cool. I highly suggest, if you have not, check out the Brickman Machine Shop or the Summer Machine Shop. They have some really, really cool machines. And that hallway in Gleason, that's all glass with all the machines on the side. Read some of those descriptions. They're actually pretty crazy. And we are able to do that here, and we have a couple of projects going on right now that include designs of experiments for CubeSats. We are not at the point where we're making a CubeSat yet due to funding. It takes about anywhere from $10,000 to $20,000 to launch a good experiment on a CubeSat. It has been done for $250, but it was honestly just like a cube with a couple of PCBs thrown into space and just communicating, which is still very impressive. But we're going to try and go for something that has a little bit more scientific merit. And CubeSats range, their prices range. As I said, you can launch one for $250. You can launch one for $2 million. It's really, really up to you and what your funding, what the funding is behind you. But the biggest problem is research and development. It takes a long time to really prove that what you have has merit to the scientific community, and you have to submit a proposal to NASA, which is quite lengthy, and then you have to go through about it a few months, maybe 4 to 5 months of selection, and then another phase of study, and then eventually you'll get funded to get that launch. And the whole funding really is just the launch. The whole launch is free, which is fantastic. You don't have to pay for anything. You literally just hand them this, maybe an assembly packet of some sort, and then they say, okay, cool. We'll put it in the rocket and we'll get shot out during our next mission. So they've been doing that since, I think, the late 1990s. It's really taken up recently, and a lot of the universities have started to do it. And of course, we're able to test crazy things like solar sails, where the distance from here to here can be about like 15 meters or something. And even larger. There's actually a solar sail senior design team doing it right now, where their solar sails are about 30 meters. And they will actually be here at Imagine RIT in the Gordon Fieldhouse right next to the RIT SPEX exhibit. So if you want to see more about that, we'll have the thing fully deployed. It will be really, really cool. Definitely come by and see that. But really what they're doing here is this is something called Mylar. It's a very, 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 very highly reflective material, and it's very, very, very thin. So it has a great combination of characteristics for solar cells. One, it's highly reflective, and two, it's very thin. That makes it able to be packed, a lot of it to be packed in such a small volume as you can see, this is this is a 2U cube satellite. So or a 3U cube satellite. So it's only got 20 by 10 by 10 by 10 centimeter, 20 by 10 by 10 centimeters of volume to store all this in it. And it has to also have a deployment section. It has to have a rigidity up section, and that means that there needs to be something there to keep these booms deployed at all times. And different CubeSats do different things. Some have deployable booms. Some have spin stabilization, which is a really cool thing where during deployment, they release these panels. As you can see, they're flapped up, and they stick out the solar cell a little bit, and then they start to spin. And angular momentum takes care of the rest. It just spins out like crazy, and then it slows down as it gets larger and larger. And it's a really, really cool effect. And they're really interesting. They're just kind of getting to the point where they're going to be used on bigger space missions. But as I said, the problem with these solar sails, not really a problem, but one of the hindrances with these is the amount of propulsion that you can get from them. From a solar sail about this large, you can probably get maybe 1 Newton of thrust. And of course, that's very low, but over time, that does a lot because it's a constant 1 Newton. It's all the time. As long as the sun is directly incident on the surface, you can get that. Now, of course, that doesn't always happen, which is why some very forward-thinking cube satellite teams have been able to contract and retract these so that when you go into the sun, you're not getting the opposite. Because just as it is reflective on this side, which is the side you want to be hit, it's just as reflective on the other side. So if you go into the sun, you'll have reverse thrust, just kind of counterproductive. So what they do is they'll retract it and then contract it again, or contract it and then they'll expand it again once they're ready for thrust. This is a really cool idea that's being actually worked on at RIT in two different fashions, one in the research and development stage and one in the fabrication stage. So it's really, really cool. And we'll also talk about the possibility of interstellar travel with solar sails. We talked about this last year a little bit. There's this thing called the Starshot program. It was theorized, I think, by Stephen Hawking, or endorsed by Stephen Hawking. And he said that it would be theoretically possible if we were able to create a solar sail with 0.99999% reflectivity, very, very reflective, not really possible at this point. I think they're expecting the project to officially start in 2021 or 2026. I can't remember. I know it's a bit of a gap, but it's something. And what they're trying to do is they're going to have this really, really reflective solar cell with a very, 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 very small payload, actually the size of a silicon wafer. If you've ever walked through the Micro-E building in Engineering Hall, the Micro-E Hall in Engineering Hall, you can see all the really interesting stuff they're doing with those microelectronics. And they can actually make these really small chips. Now, obviously, it's not totally complete because they still need to be able to embed a lot of really important communication protocols and all these things onto that small chip. But assuming they can do that and we can get the structure made and with the efficiency that's necessary, we can accelerate one of these things to 20% the speed of light. And that's represented in this scientific notation as 0.20 c, c being the speed of light. And basically, that just means it's going really, really, really fast. And there's some cool phenomena that happen when when things start to travel this fast in space, that is between the object and its destination actually contracts. This is due to special relativity and how mind-bendingly awesome it is. So it's a really, really interesting proposal. It's definitely something that's being investigated. It is not at the beginning phase yet where they're starting on the actual fabrication. They're still in the research and development. But it is a really, really interesting proposal. And they're actually planning to send one of these things to Alpha Centauri, in which the travel time would be 20 years, opposed to a traditional satellite with a travel time of 30,000 years. So a good amount quicker. And definitely keep an eye on that for future development, but that's coming up. The development in solar sails, I think I already went over this, but it's mainly being experimented with CubeSats and small sats, just two different types of satellites. And it's currently, a lot of people are doing it. The senior design team here is doing it, and it's really just undergoing the research and implementation stage at this point. Yeah.
In 2010, the Japanese space agency sent something to Venus solar cell.
Oh, really? Oh, I didn't know that. Okay, very interesting.
They kind of lost control after it. They made it to Venus.
Very cool. I didn't know that. Very cool. Yeah. So as you heard, it's definitely being used. People are really starting to take up with it. It really went on the rise earlier last year after this Starshot program was theorized. People were like, "Whoa, this is really, really cool." And they started investigating it themselves. There was a phase 1 NIAC study, which I talked about earlier, that was granted for a research study here at RIT. So one of our professors will be doing a solar cell study with a bit of a twist, in the sense that he's going for more like a Starshot thing, where you basically take this chip, throw it into space from out of the International Space Station, and it literally means a Russian cosmonaut chucking it into space and then taking a laser and going like this, and it just accelerating like crazy. It's a really cool idea. Again, it's a first phase NAC study, so it's just a feasibility study, but it's very, very cool, and it's definitely got a lot of interesting things that can come out of it, and then we'll really be looking forward to that. But mainly right now, I think for most Cube satellites, they're using it for station keeping propulsion, because as you may or may not know, for vehicles in low Earth orbit, the atmosphere is not totally zero in low Earth orbit. There is a little bit there, and over time it does take effect on your orbital velocity, and it will cause you to re-enter the Earth's atmosphere, which can be very harmful for your health if you're not careful. And basically this keeps them in low Earth orbit by increasing their orbital velocity over that time. And it's mainly used in CubeSats. I don't think they're ready for putting it on human spaceflight missions, just because of the efficiency problem and the fact that a rocket, a hydrogen thruster, is significant. There is a cool video that we can try and watch about the expansion and contraction of these solar cells. It's just a demonstration. It's nothing crazy, but it may just give you guys a better sense of what's going on. So this is a project that's being researched at a company called RIT. I think it's French, so they pronounce some letters and don't pronounce the others. I'm not really sure how that works, but as you can see, it's a very interesting type of deployment. They are using the deployable booms. So these things here, so they're not doing the spin that I mentioned before, but it's very, very cool. And I think they said their square footage, or not square footage, the area in square meters of this is 10,000. It's crazy. I believe this. I don't think this is a CubeSat form factor, but it is definitely very close, and it just goes to show you. This video really just shows you how immense this solar cell can be from such a relatively small box. So if you have something maybe this big, whereas something that this big can deploy 30 meters of it, something this big with a very efficient packing volume and efficient density, you could get to hundreds of meters if you're good at what you're doing. Space is nice in the fact that it's not really creating a lot of structural stress during deployment, so deploying it can be a little bit easier for a vehicle, whereas on Earth, you have that constant thing called gravity that's a really annoying thing to deal with during deploying these huge arms. And this is kind of what they're going for here. They've obviously done a lot of work on this, and hopefully I think they have commercialized this to a point, so you can actually go online and buy a solar cell. So you've got like $20,000 in your pocket, and you're like, I have nothing else to spend.
That's not so scary, right?
That is to scale. Well, not with the Earth. No.
I was like,
with the sail to the CubeSat, yes. With the Earth, I think they just probably took an image and dropped it in there, but no, I don't believe it is to scale. Yeah, the Earth is.
That looks like it could like cover all of Australia.
I know. Yeah. No, it's not.
Block out the sun.
Yeah. What's up?
I, for one, welcome our solar sail overlords.
We always do this.
wait, are we all? Did Mr. Burns bring it?
Yeah.
Okay, so does anybody have any questions about the solar cell stuff before we let Amber talk to us about her phase 1 NAG studies that she did at NASA? No? Okay. I'll leave it to you. It clicks.
Awesome. Hope I don't mess the cookie thing up. Like James said, my name's Amber. I co-opted at NASA for 6 months, and one of the missions that I worked on was this mission called Float. Now, we talked about NAG proposals, right? And now most of these are NAG proposals, NASA Innovative and Advanced Concepts. So you think about what you think about like Star Trek, and you think about Star Wars and everything that happens in those movies and TV shows, and you think, that's so far off, so weird, right? Like that's never gonna happen. Well, with these proposals, it's kind of like NASA's way of getting a home run on the first hit, right? There's a lot of stuff that is not feasible, that is science, that becomes science fiction, or people think of, and it's just not feasible in physics, basically. But NASA goes, well, what if you took those ideas and maybe one of them is? Maybe you get that home run hitter. Maybe that terawatt laser on Earth sending a spacecraft to Alpha Centauri using a solar sail, maybe that's a really good idea. Maybe that's our home run hitter. So they give a little money to these projects, and they give a little time. They say, show us how. So when you talk about NIACs, they're all public, so you can see all of them. A lot of them get covered in like space news, if anyone's into that kind of stuff. A lot of them, I saw one for a Titan submarine, a submarine that goes onto like the Saturn's moon, and it's like a submarine. But what's weird about Titan is the oceans. Does anyone know what the oceans are made of there? Yes. So it's way different. So it's a submarine in an ocean of methane, and it's crazy, and it has to like come back up and be all autonomous because we can't send anyone. So a lot of these NIAC proposals are pretty far out, right? Like submarine on the Titan, we haven't even really been to Titan yet, so that's a little far out. And they think, okay, like 2040 we'll have this kind of stuff. Well, this NIAC proposal is a little different. My boss is one of those idea guys, he was one of those idea guys that he comes up with ideas and but we could do this, and rolls with it. So these next two proposals that I'll talk about. See, I messed up the clicky thing. He came up with both of these, and I was an intern like researching. So let's talk about the proposal, right? So float, it's not floaty. It looks like floaty. I know it looks like floaty. I would like to call it floaty. I think that's cuter. But the mission's name was Float, and it stands for Phobos. It stands for Phobos. Oh man, now I'm just. Basically, Phobos operational tethers. Or Phobos hover on L1 operational tethers. And you can actually look Float up. Now we have this really cute little logo in the corner too. But basically, the idea was, does anyone know what a Lagrange point is? All right, we'll go on the back.
So as I understand it, it's the point where at least, I know L1, 2, and 3 are the points where the gravitational forces of a body and a body orbiting said body will allow whatever object placed in them to orbit the stationary.
Kind of, yes. So yes, that's part of it. But the very general definition of a Lagrange point is it's basically where the gravitational and dynamical forces cancel out in orbital mechanics. Now, I'm not going to teach a course about orbital mechanics. I took one. I'm not going to do a 12-page proving this to you guys. But if you ever want to look at the proof for Kepler's equation, it's a good time. But what you can do here, so think of gravity. Everyone know the theory of like space-time, right? So when you think about gravity, you think about gravity well. So if you look at a black hole is like basically a RIT in space-time. So you have think of a flat sheet, and that's space-time, and you drop a bowling ball on it, right? Have you ever been like the skinny kid on the trampoline, and then all of a sudden you're like your friend comes in and just like brings it all the way down, just jumps on it and just sends you flying? Well, that doesn't really happen, but definitely the dips happen, and when you step on the trampoline, right? Same thing with space-time, right? So the L1 points, well, the Lagrange points, there's actually 5 of them, are actually the top of the gravity hill. So if there's like every time there's something with a huge amount of gravity, there's this dip in space-time, well, there's going to be a little hill, right? Now, the cool part about Lagrange points is that because it's the top of the gravity hill, everything to keep in orbit has to constantly have propulsion, basically, or it will start deorbiting. If you're on an L1 point, you don't have to actually keep yourself in orbit. The 3 and 4 points are actually stable, so you'll find a ton of stuff there on 3 and 4. And I'll show you a little bit of a diagram later on this after the presentation if there's more questions with this. But what's the cool part is you can stay on the top of this gravity hill. Here's the thing. Have you ever tried to keep a marble on top of like a hill, right? You have to like keep adjusting it because it's never going to stay perfectly on there, right? Well, the Lagrange 1 point is actually, and Lagrange 2 are actually unstable. So you have to constantly do very fine station, right? So you get, this is like an artist rendition of it. So this is Mars and this is Phobos. The L1 point is somewhere in between Mars and Phobos, like directly. And when you think of Phobos, so Phobos is Mars's moon. When you think of Phobos, you know how our moon, you always see the same face? Same thing happens for Phobos. Does anyone know why that is?
Because it's tightly locked?
Yes, because it's tightly locked. So Phobos is the same exact thing. So you always have this weird thing called the Stickney crater. I'll show it again later. That is always facing Mars. Now, what if we took a spacecraft? This was my mentor's big idea. He said, what if we took a spacecraft with existing technology that we have today, and we balanced on the L1 point, right? We do very fine station keeping with very small thrusters, with very accurate position data that you're accumulating, and you could just float on the surface, right? And then what you could do is you could lower a sensor package with a tether, right, and get surface data. You could park on the surface. You could get data at different altitudes about the environment around Phobos. Phobos itself is only like 25 kilometers, like lengthwise, and widthwise it's like 11 kilometers. So it's very weird. And you kind of have this like fishing analogy, right? Where you have this the bobber on the L1 point, and then you're lowering the hook or a sensor platform. Okay. And the timeline for this was actually 2026 is the projected launch for this kind of thing, because NASA wants to take to Mars in 2030, right? And we'll talk about that next. But the cool thing about Phobos, right? We know very little about Phobos. So why would we want to go to Phobos? First of all, the Russians were obsessed with Phobos for a while, sent 3 missions there. None of them were succeeded. Almost kind of comical for our Russian friends. But Phobos is actually seen as, does anyone go on a long road trip recently? Like pretty long, like over like 3 hours?
Oh.
All right. Did you guys have to stop and fill up for gas?
Not typically.
No?
I filled before.
Okay, but has anyone had to stop and fill their tank up with gas? So why don't we do that with space travel? It's way more efficient for us to go. The delta V required to get to Phobos is a lot less than the delta V required to get into Martian orbit. So what if we stopped at Phobos? We think that there's awesome resources there, like water, somehow, you could mine it, or different materials, right? And then you just kind of fill up there, and then you just take the hop to Mars, right? Now, there's also a lot of stuff that's cool with Phobos is no one really knows what happened with Phobos. It's very weird. It's weirdly shaped. People think it could be a captured asteroid. They think that it could also be like our moon, where they where like there was a collision on Mars and then it got knocked off, right? Or there's also a thing where Phobos is basically covered in like red dust, so it may be more efficient to go take a return sample of Martian dust from Phobos instead of going directly to Mars. So that's why you go to that's why Phobos is so interesting. And actually, this would be float would be like a precursor mission to that, right? Or sending humans, right? So you don't want to send. Who wants to go to a place where no one has ever been? Okay, I don't want to go to a place where no one's ever been or even knows about. Like that's like saying like, hey, I'm gonna go deep as far as I could into the ocean, blindly, not knowing what's going on. Like I don't know about you, but I don't want to do that. Like, and NASA as an organization or really any space company would not want to do that either. So there's a lot of stuff that we don't know about Phobos. We don't know about the radiation environment. There's a lot of micrometeorites around everywhere. There's, like I said, what resources are actually there? We don't know because Phobos is so small compared to Mars that it's really hard to get data about it just from telescopes and astronauts. So let's talk about a little bit about the spacecraft itself, right? So here's this nice Stickney crater in this nice drawing. Here's Stickney crater, and that other side, Mars will always be facing, right? And you'll have the main spacecraft here, and that'll be balanced on the L1 point. And you can lower, well, near the L1 point because the L1 point is actually has to be at the center of mass of the whole system. So it could be approximately there. But this is what's controlling where you are. And you lower the tether, and you have a sensor package at the end of the tether. Now, how long is this tether? 6 kilometers. That sounds like a lot, but actually, it's not. Because Phobos is so small and very close to Mars, relative to the other moon, Deimos, actually 6 kilometers is weirdly close for an L1 point. So float can be pretty close already in the main spacecraft, and 6 kilometers is not that long. They've done kilometers that are like 30 in space. Yeah.
So put it in perspective, I held a spool of fiber optic cable that's 2 kilometers in my hand.
Exactly.
So
exactly, it's really not that long. And when I talk about a tether, right? When you talk about a tether, it's literally like a fishing line. It could be literally like about that size, and that's actually what we were looking at. And you'd be able to reel the tether in and out, and you could get different data from different altitudes, which would be nice, right? Again, I already kind of talked about this. It's the radiation environment, particle environment, what resources are there, landing sites. We didn't just go to the moon and be like, okay, where am I going to land now? No, that's not what we did. They were looking at it. They were looking for potential landing sites before the Apollo missions even got. Gravity mapping and density. The density of Phobos is very weird. It's not how it should be for something that's like that small. So they're wondering what's under the ground, and they want to be able to map the density of it. And again, composition and subsurface. There may be aliens there. You don't know. There could be something we find there as well. And these are just the sensors that kind of do all those things that I talked about. You have your dosimeter for radiation, imaging cameras to take pictures. One can also be on the other side of the spacecraft because it will be orbiting Mars, just in a more focus on Phobos, but it will be orbiting Mars. So if you face the camera the other way, you could be used as like a weather satellite for Mars and communications with Earth. But so the parts of float that I basically worked on was designing like this feasible spacecraft. Now, the size of float, this thing right here is about 1.2 meters, so about right here-ish. And this is about, we talked about CubeSat, it's about 9 CubeSat, which is very weird. It's like 10 centimeters in like a circle around about this big. Now, what are these parts, right? We have the part that's the main spacecraft, which we affectionately call the Mars Observation Monitor, or MOM. And we have the tether, and the MOM has all the power.
Yeah.
And I'll talk about that. The MOM does, yeah, right. But she provides support for what we affectionately call the POP, the Phobos Observational Platform. There was actually something we were working on to throw into the proposal, something called a SUN, a Surface Observational Node.
Is it a goal for all like astronauts to make everything a nice acronym?
Yeah, so NASA's really big on acronyms. Sometimes the acronym, I worked on another mission called GPX2. That was weird because it didn't actually stand for anything. It was about GPS, but it was like, I was like, what does GPX2 stand for? And he's like, my boss was like, no, being different, we're not using a backronym. Then my other boss was like, Mom, Pop, Son. They told us daughter was too long of an acronym.
So, when you're planning these sorts of things, and you're really getting together, and crunching a lot of math and doing all that stuff. It's important to like sequence this out so you can stay like on pace, on budget, and all those sorts of things. What percentile is spent in coming up with clever acronyms?
Wait, spent in what?
In coming up with clever acronyms.
Oh,
what's the time budget for that to make sure that
okay, actually, I'll talk about that. I'm gonna wait, and I'm gonna talk about that for actually the next project I'm gonna talk about. Because there is actually some funny stuff that comes up with that. But because I want this to be a little bit more fun and weird for you guys, right? But yeah, so the tether, you may ask why we've got these huge ass solar panels, right? Well, there was this whole thing about, do we take the all the power just from the MOM and just send all the power and data through the tether, through the POP? And we decided against it because actually, when you have a really small like diameter tether, there's a ton of micrometeorites. What if the tether gets cut? Now your mission's over, right? You want to have these backup redundancy. So if the tether gets cut now, because we have our own power system on the POP and we have our own communication systems between the MOM and the POP through radio, if it gets cut, maybe the POP's just on the surface, but we can still get data, right? We can still get useful things. And the mission length is about 1 Martian year. That's like 2 Earth years because Mars is farther out. The other thing weird about the tether is even if 1/2 of it got cut, for power you have to do a line there and back, unlike on Earth, where we have the ionosphere, and you only need basically a line down. So we decided to go against that. Honestly, if you wanted to learn more about this, I can talk about it. You can ask me questions. You can look up Float. The report is 100 pages, and it's going to be, it's not out yet, but it's because everything that is done NIAC-wise is publicly published. So just look up NIAC, and it's there. If you want to learn more about it too, look up the NIAC Symposium. My mentor went and talked at it this week. I mean, not this week, this year. And they asked a lot about space tethers. They were all just like, "Yo, why don't you just like park on the surface and become the first space elevator?" And my mentor got really like sweaty about that. He was just like, "No, that's not the point. That's not the point. Why are we doing a space elevator?" And then he came back and we were all just like, because we live watched it, and we were like, "Yo, that space elevator video really cool." And I've never seen a grown man cry. But yeah, you had a question or?
You can
EOTR? I did not. Acronyms was not my specialty. Although I did come up with some good ones in my day. So, like I said, check out the NIAC proposal, check this stuff out. It's just really cool. If you ask me, I had a good time working on it. So, all right. So let's talk about the other idea. Disclaimer, I didn't really work on this one. My roommate actually worked on this one, and there was actually this was not a NIAC proposal. This was a mission for new technology that GCD was funding. And, so we talk about, do you have a question?
So is this the home for Mark Watney, the pirate king of Mars?
Yes, or if you think Matt Damon, all right, like if we're going for the Martian. So when you think about, so the last proposal was all about, hey, we want to help, it's getting toward that goal of getting to Mars. Well, what do we do once we get there? So we have Mars Ice Home, a new home on Mars. And I have some really nice pretty pictures because my mentor really liked getting pretty pictures done. It makes it easier to do presentations like this, right? And you can look at this little igloo. So what is Mars Ice Home and why would you do Mars Ice Home? Why I talk about the acronym thing though is when he was coming up with a second proposal for Mars Ice Home to do like a deep space ice home, which I do have a thing on that later. He asked myself and another intern to come up with acronyms, and it's a lot harder to come up with acronyms than you think. We spent maybe half a day coming up with acronyms. So if anyone says that I worked hard at NASA, I probably shouldn't say that. But so Ice Home, basically, the problem with like long-term human missions is there's a lot of radiation. Our atmosphere is really nice to us, so it's really great that we're not killing it as much anymore. So basically, a lot of the current plans for if you had a deep space mission to Mars, you would just dig a hole underground, and the astronauts would live underground. Now, but do you really have to do that? So actually, if you had these spheres that were inflatable, so Mars Ice Homes are inflatable. This is like a concept drawing of it, and you could take these inflatable homes, you can go to Mars, where Mars is supposedly supposed to have water underground, mine that water, and you could you could literally inflate your house, but with water. And even a meter of water, like drastically reduces the radiation that you would receive if you're in this home. So the water ice serves as a shielding from galactic cosmic rays, which basically just come out of nowhere from different stars. I'm not too versed on that kind of stuff, but they're pretty dangerous to human health on long-term Mars missions. So you come up with this. He came up with this design. Also, too, if you don't have to bring the building blocks of your home because you're inflating it with water, basically, that's a lot lighter, a lot more efficient. It's really expensive to get shit up in space. I'm gonna be honest. I don't think I should start. Sorry. But it's really expensive, and if you can go there and get most of that back, like just from where you are, that's so much more efficient and so much more cost-effective. And obviously, you see it's multi-layered, so there is like a protection of material, like radiation material. There's also CO2 insulation, then water, and then like this like kind of nice structured thing. As you can see, he's lounging. He's an astronaut. He's happy. All right. So just some facts about this. The pressure inside the habitation area would be 14.7 pounds per square inch, and it would be a comfy internal temperature of 72 degrees. My roommates don't let me even get up to 72 degrees, so I'd rather live here right now. They keep it at like 67, and I wake up. But so the whole point is to make astronauts feel more comfortable. There's a lot of psychological issues, so radiation aside, if you're trying to protect them from radiation and you just make them live underground, how do you think that's for like 2-3 years? How do you think that's going to affect their mental health? There's a huge psychology study on that kind of stuff too. So the cool part about this is everything is translucent. So it's not like you're living in a dark cave. You're living in a nice little igloo, right? Like an Eskimo. And the radiation, like the suits that astronauts wear that are radiation protected, they go out. Have you ever seen an astronaut's hands after they've done a moonwalk? They're all blistered. Everything. It's terrible. It's because the pressure difference is really hard to work with. Like think about you're wearing clown shoes and clown gloves, or like the Mickey Mouse gloves you get at Disney, and you're trying to actually do science, and you're trying to actually work on equipment. It's it's terrible, and that's why they have all this training and they go through a lot of that. But with ice home, you'd have a place that was pressurized, that you could take your suit off, you could do everything, and you'd have like a workplace, a science base, and a lab to actually do the work that you need to do. And you wouldn't be field trapped in a cave doing it. Again, pure water ice. So there was a lot of study on my roommate, which she actually worked on, was studying how much ice to water, because it's not really like water ice, it's like a slushy. How much ice to water actually would be the optimal radiation protection. And she basically wore a dosimeter. I saw it was like on her lanyard. She wore a dosimeter, and they like bombarded like these bags of ice that they would like freeze for different time periods, and like wanted to see the effects of like radiation. So that was pretty cool to see. She showed me her lab once. So it's, like I said, pure water ice acts as the fill material for the ice home shielding and structure. The primary insulation layer between the water cells and the ice cells would be a carbon dioxide gas layer, which is already in the Martian atmosphere. So, like I said, all this stuff is here. We don't got to bring any of it with us. And, I don't know, this looks like a nice floor plan. This is bigger than my apartment right now. So, now, then you get a really nice, this just looks a lot better. And then if you're my mentor, this is the Christmas version. He sent me this like near Christmas, and I just it was the funniest thing that had happened to me in like forever. I loved it. It's so, send this to your family from your nice ice home. You got Santa's alien sleigh. There's some nice wreaths. Even the rover over here, man, they've got Christmas lights going on. So a new home for the holidays. So what's next from Mars Ice Home? So what they were trying to do was go for a NIAC for a deep space ice home. Now I could not find any of the pictures online for this because all this is public information. What I'm presenting is all public and has gone through all like the ITAR and stuff. So I couldn't find any public information, but I've seen a picture, and it's basically like a torus. And what you can do is you have that ice home structure, and you can bring it into deep space stations to like an asteroid, and then you could like spin it to like have artificial gravity, and like you'd have that radiation protection and the artificial gravity, and you could inflate it at the asteroid. So like itself, if it had the right resources. So they were working on getting that kind of proposal. Shout out to Kevin Kempton. He was my mentor, and he came up with both these ideas. And he let me work on this really cool project. So shout out to him. And
there's a reference to slide.
Yeah, it's practice.
If you guys want to find any more information about these, you can go to NASA. The NASA website is both where I got those proposals for evacuating the ship and the radioisotope questions. So it's all publicly available, as we said. A little bit of digging. Really cool stuff going on.
Yeah. Any questions, or you guys sick of hearing us talk? I get that too.
That's all for us. If you guys have any questions, please feel free to reach out to us. You can also reach out to us at specs.rit@gmail.com.
And also, like, if you guys are interested in space stuff and actually working on space technology, that's what RIT SPEX is all about. So I would encourage you guys, if you are interested in that kind of stuff, we take all majors. Doesn't matter what major you are. You could be creative writing and want to work on stuff.
When and where do you guys meet?
We meet at 11 a.m. on Saturdays. Not earlier because we tried that already and it didn't work. 11 a.m. in HLC. Room number
2575, 2585.
Yes.
It's a weird room that's made up of two rooms sometimes.
And those are our general meetings, and we do a lot of workshops where we have presentations about stuff. We teach people skills. We've done coding workshops for people who don't know how to code. I've given one on orbital mechanics before. There's paper CubeSats. We had the talk last week was space junk and space debris. So if you're interested in this kind of stuff, even if you just want to learn, or if you want to join one of our projects that James mentioned a little bit about, you can come to the meeting. People who work on the project will be there, and then you can talk to them and you can join up if you'd like. Even this late in the semester, we can always. That's our pitch. Thank you for letting us see the pitch. What? So I'm a mechanical engineering major. I'm in my 3rd year, and yeah.
I'm also a mechanical engineer. We're not all mechanical engineers. That's a good 60% of us, but we have plenty of CS.
It's not 60%.
It's like 60%. We have a bunch of CS majors. We have a bunch of SE majors. We're rounded out. We have a good amount. We don't have any liberal arts majors, but
we wouldn't turn any away. We actually encourage. Even if you don't want to work on projects, you don't care about space exploration. If you like stars, you like using telescopes, we do that too. We have the fastest tracking telescope on campus, the same telescope size that the RIT Observatory has. Our advisor does a lot of work at the RIT Observatory, and she's kind of jealous that we own this one, and she doesn't over there at the observatory. So we do a viewing party, we have star parties. Not this as much this semester because it's been kind of cloudy and cold, and but we do bring people out, and you get to actually use the telescope. We can look at whatever. We try to take pictures. We have multiple telescopes, and that's a fun time too. So if you don't really care about space exploration or these kind of cool missions or working on space projects, you can work on that kind of stuff. Just come out, see the stars, talk to some cool people. All right, thank you for having us, guys.
thank you.
All right, let's give our friends at Specs another hand. So just a couple quick closing announcements. If you want membership or to buy Avengers tickets or sodas, talk to Tulio, our wonderful ops officer. If you have to poster, pick up your posters in the front. And come to Toricon this weekend.
Yay!
We still have some time left, so if you want to mingle, feel free to do that.
We'll be in Clark A for Toricon.
Yeah, we'll be in Clark A.
Claire is with us. It's a good time.
Or come watch the chess show as well.
Yeah.